Okay, if you have a look at the diagram, you've got rectangles with length 1 and heights different all along there, and the rectangles are all above the curve being y equals 1 on x. So if I look at finding the area of those rectangles, you can see that this is the height. So each one of them is length 1, like a width 1. The height, I just put in the 1 and I find the height, the y value, so 1. So if I look at that, I've got 1 plus, if I look at the height of the next one, which is when I sub 2 in, I get a half, so half times 1 is a half. If I put a 3 in, I get a third, third times 1 is a third, etc. If I go all the way up to some value n, remember it's still a width of 1, and the height would be 1 on n, so I'd get 1 on n. Alright, now that is always going to be greater or equal to the actual, so the exact. So if I go between, I'm going between 1, because we're starting at 1 here, and n, if I go between 1 and some value n, and the curve is 1 on x dx, what do I get? Okay, so 1 on x, when I integrate, that becomes a log, and log x between 1 and n, and that equals log n minus log 1. Log 1 is 0. But what I am, yes, so sorry, I did make a mistake here. So that should be n plus 1, shouldn't I? I should be going between 1 and n plus 1, because when I put the 1 in, it goes between 1 and 2 is the rectangle there. So when I put n in, it's going to go between n and n plus 1. So I'm finding the area under the curve between 1 and n plus 1. So let me just change that, and then we will get what we want, which is log of n plus 1. So, so we can see that this has to work, this inequality here. And then by what do you conclude about the infinite series? Well, if you look at that right-hand side, it's log of n plus 1. I can keep putting higher and higher values in for n. There's no end point to the higher value I can put in for n. I can keep going forever. So if this side is greater or equal to that side, then this side must also, that left-hand side must also become infinitely large, because the right-hand side does.